Welcome to Pre-Calculus. Today we will continue investigating various discontinuities in functions, focusing on classifying discontinuities as a jump, infinite, or removable discontinuities, as well as finding limitations of graphing calculators in the way they represent discontinuities. Let's head over for our last two examples. We saw one example of a jump discontinuity. And let's take a look at two other functions that show some sort of discontinuity. So we'll head over to our notes. So again, two tasks. We want to start by graphing the function by creating a table of coordinate points. So I'm going to start off by creating the t-chart. And we'll place our x value in the left column there. And let's give ourselves the values -2 through +2. So -2, -1, 0, 1, and 2. And we want to calculate f at x for this function. F at x equals 1 over x squared. So let's graph this one manually. I'm going to evaluate the function at -2. So f at -2, I'm going to place that -2 wherever I see x. So I need to be careful to put that in parentheses because of the negative sign. So it's 1 over parentheses -2 to the power of 2, which is 1 over +4, and that gives us the decimal 0.25. We'll now evaluate for x is -1, so f at -1 is 1 over parentheses -1 squared. So that's 1 over +1. -1 squared is +1, which is just 1. We'll calculate it f at 0 is 1 over parentheses 0 squared, which is 1 over 0 times 0 is 0. And again, we can't divide by 0. So what we would say is that that value is undefined. We'll see how that features on the graph of this function f of x. Well, let's keep going. F at +1. And see if you can predict what the output will be here. So I'm putting a 1 down there in the denominator. So 1 over 1 times 1, or 1 squared, is 1. So 1. So again, I'm seeing a symmetry here around that undefined value. Let's see if we see another symmetry. What do you think f at 2 will be? 1 over parentheses +2 squared equals 1 over 4, which is again 0.25. So if we were talking about function symmetry, this would look like even symmetry, something that's reflected around the y-axis. Let's list these coordinate points over here on the left. So I got -2, 0.25, -1, 1. 0, 0, in fact, is undefined. And really what we'll see is that represents a vertical asymptote right on the y-axis. On the right side of that asymptote, we have the point 1, 1, and then 2, 0.25. Let's place those points. So here at -2, we're up at 1/4. At -1, we're at +1. At the y-axis, it's undefined, so we're going to have a vertical asymptote. On the right side of that y-axis vertical asymptote, we have the point 1, 1, and then 2, 1/4. So again, that's the framework. And let's go over to our graphing calculator just to see what that graph will look like to fit it in the framework. So I'm going to type in f of x equals 1 over x to the power of 2. And definitely the graph has that appearance of two pieces that come up towards the vertical asymptote at the y-axis. Let's fill in on our graph. So I'm going to pick up and place this graph. So we had a horizontal asymptote at the x-axis. And then the graph descends from the y-axis and flattens out as it heads towards infinity. End behavior, both sides is towards 0, y value of 0. Now, we've done that first task. At this point, we want to classify the discontinuity as a jump, infinite, or removable discontinuity. So if I think about that first discontinuity, we saw the jump one. As these two sides approach the y-axis, do they have finite limits or are they infinite? Really, we got to think about what would be the meaning of those arrows that indicate it keeps going forever. Really, that indicates that we're at infinite limits. And really, that says what kind of discontinuity we've got. So if we go back to our definitions, an infinite discontinuity is if the left-hand limit does not equal the right-hand limit or both sides have infinite limits. So that really describes this f of x equals 1 over x squared. Both sides have infinite limits. Therefore, this is an infinite discontinuity. And I just want to highlight that this is different from what we saw with the jump discontinuity, because on the jump discontinuity, these are finite y values. They end at some finite number. Okay, so we've seen two of these. Let's take a look at a third example. So here I've got the function f of x equals x plus 2 over x squared minus 4. Now, before I start filling in the table, I'll go ahead and create the table. So we've got it here in view, x and f of x. I want to do some algebra in advance to see what's going on with this function above and below. And specifically, I want to factor anything above in the numerator or in the denominator. So as I look at the numerator, there's not much to factor there. So I'm just going to record that as x plus 2. In the denominator, though, we've got an original function of x squared minus 4. Now, you may recall from Algebra 1 and Algebra 2, that is the pattern of a difference of two squares. So just to remind you about how that looks, if I've got generally a squared minus b squared, that would factor as a plus b times a minus b. Let's go ahead and use that pattern of the difference of two squares to factor this denominator. So again, the numerator is just x plus 2. But the denominator, if I take x squared and take the square root, that's x. And then the square root of 4 is 2, so it's x plus 2 times x minus 2. So that factors that denominator. I'll pause there for a moment, and I'm just going to ask you to consider, what do you notice when you compare the numerator with the denominator? What do you notice about that factored form? Excellent. We have an identical factor above and below. And just like with numbers, if I have something divided by itself, for instance, 2 divided by 2, just to think of numbers, they would cancel out and leave 1. Factors do the same. So I'm going to cancel those x plus 2's. And I need to note really that that is a place on the graph that in a way falls out, but the graph still doesn't exist at that x value. So I need to find that x value that would make this x plus 2 equals 0, and we'll see that on the graph at the very end. So I'm going to set that factor that canceled equal to 0. And really what I'm claiming is that it can't equal 0. Remember, if I have a 0 in the denominator multiplied times other things, it'll make the whole denominator 0, and it will become undefined. So I'm going to subtract 2 from both sides to see what that x value is. So I'm looking at this value at -2 that's undefined. Okay, so we're going to hold on to that. And at this point, what we're going to work with in terms of our table is the simplified version of this function. So when we canceled out those x plus 2's, what's left for us is the function f of x equals 1 over x minus 2. And we're just going to keep in mind the cancellation told us that this x does not equal -2. At -2, the function's undefined. Okay, so we're ready to start filling in our table. So instead of going -2 through 2, I'm going to back up. Let's say we'll back up to -3. So we'll go -3 through +2. And since we do want to investigate what the calculator is doing in terms of showing that undefined term, I'm going to head over to Desmos. And in fact, what I'd like to do is, we did have a nice kind of simplified form down here. I'm going to go ahead and type in the original because I want to see how is the calculator representing that value at -2 that we saw cancel out. So let's head over to the calculator at Desmos. We'll clear out our previous example. So I'm going to type in f of x equals numerator x plus 2 divided by x squared minus 4. And there's that graph. I do want to compare it with what we found. In fact, let's call this g of x just so that the calculator doesn't get confused. The one where we canceled out x plus 2. So it's 1 over x minus 2. And notice those functions are virtually the same. If I turn that green one off, you see the blue one, turn the green one on, it's really the same graph. So it shows us we kind of saw something when we canceled out the x plus 2. But let's get a table of values. So I'm going to hit the cog. I'm going to go to the original function. And we see that that -2 value is undefined. I do want to put in -3 because that's where we had started our graph. So -3 is here at -0.2. -2 is undefined. And what I want to notice here is that on the graph itself, it doesn't look like anything's changed. But when I click on the graph and move that cursor to show points, when I reach exactly -2, the calculator is telling me that that is undefined. And notice it becomes an open circle right at -2. Now, if I hadn't done that, the calculator looks like it's nothing different. So I have to kind of keep my eyes open in the table and with that algebra we had done initially. We're looking for something to cancel out. Well, let's get this graph. So at -1, it's -0.3 repeating. 0 is at -0.5. 1 is at -1. 2 is undefined. So I do see that that's a vertical asymptote. I want to go then past it. So 3 is at 1 and 4 is at 0.5. So it's got that symmetry that we've seen with some other values, other rational functions. Well, we got what we need from Desmos. And I'm going to head back to the notes to complete our graph. So we had said we were going to take this down to 4. And let's put these values that we had gathered from the calculator. So -0.2, -2 is undefined. -1 was -0.3 repeating. 0 was at -0.5. 1 was at -1. 2 was undefined. So it looks like, given our table, we've got 2 discontinuities. So we're going to have to categorize 2 different discontinuities for this function. 3 was at +1, 4 was at +0.5. So let's graph those points. -3, -0.2, -2, undefined, -1, negative 0 point repeating 3, 0, this is the y-intercept, negative 0.5, 1, negative 1, undefined at 2, 3, 1, 4, 1/2. All right, so we're ready to plot. So negative 3 is right here below the x-axis. Negative 2 is undefined. So I'm going to put an open circle there. Negative 1 is at negative 0.3. 0 is at negative 1/2. 1 is at negative 1. And at 2, we've got a vertical asymptote. Past that, at 3, we're at positive 1. So this is on the upper side of the x-axis, and at 4, we're down at 1/2. So I'm going to fill in the graph. We've got a horizontal asymptote there. I'm going to leave that open point just so we can highlight what kind of discontinuity we have at negative 2, and then sketch in the upper right-hand branch. So we've completed that first step. We've got our graph in place, and all we need to do now is classify any discontinuity as jump, infinite, or removable. So we did note that we had 2 discontinuities. So this one here on the left, let's ask ourselves if it's one of the 2 we've seen already. So is it a jump discontinuity? So remember, jump discontinuity would say that the limit from the left is different from the limit at the right. Not exactly what we see here, because we see the limit from the left and the limit from the right coming exactly at that same point. So let's say, is it an infinite discontinuity? Well, no, they're coming to a finite value. Really, if we plugged in negative 2 here in our simplified one, after we had canceled out the x plus 2, we'd see that we have 1 over negative 2 minus 2, which is 1 over negative 4, which is negative 0.25. So it looks like they both come to a finite value of negative 0.25. So it's not an infinite discontinuity. This is a classic case of a removable. Let's remember what a removable discontinuity looks like in terms of a definition. Function has a removable discontinuity if the left-handed limit equals the right-handed limit, but not the function value at that point. And this is really a good example that we're looking at here with this f of x equals x plus 2 over x squared minus 4. The left side equals the right side. They both should come to the value of negative 0.25, but because of our cancellation of x plus 2, that point is undefined on the function. So we'll classify this as a removable discontinuity. Well, our last task is to classify the second discontinuity around this vertical asymptote. So what I'm looking at is what's happening to the y value as x approaches 2 from the left. Well, that's going to negative infinity. As it approaches from the right side, it's going to positive infinity. So already I see that that's not really a jump discontinuity, and it's not a removable discontinuity because the values are not finite. So this infinite tendency here indicates that we have an infinite discontinuity at positive 2. All right, and that completes our analysis of this function and our third example for classifying different kinds of discontinuities of functions. Thank you for joining. See you next time.